Hey everybody, this is Mr. Ainsworth. Let's greet each other properly. Good morning. And I'm here at MRWC here in Activity 1C4. And what we want to do here is just continue our discussion on the number system here. We got to a certain point here. We got up to the set of integers here. So let's just review what we already know. And then what I want to do is extend it to the rationals, reals, and the complex, and then just go ahead and analyze some different numbers, place them, and order them in their proper subsets. All right. So when we got together last time in a previous activity here in Section 1 in MRWC, we started off talking about the naturals. Okay, the naturals. And now the natural numbers here, denoted by the capital N, here start at 1 and they go 1, 2, 3, 4, 5, continuing to infinity and beyond. Okay, that's an infinite set, and we call that the set of naturals. And we talked about how it was closed under addition and multiplication and not under subtraction or division, because the results of that could be outside the set. And then we said that set is not quite big enough. We kind of need 0 here in our set, so we threw the 0 in the set of naturals. So this is the naturals including 0. And back in the day, we called those the whole numbers, in grade school. And they start at 0 and continue to infinity. So 0, 1, 2, 3, 4, and so on to infinity. That was another infinite set. And it was closed under addition and multiplication, but not subtraction, because we don't have any negatives in there. All right, you need the negative numbers to be closed under subtraction. So what we need to do is build a different set, a bigger set, if you will. Even though they're both infinite sets here. And if you include the negative or the opposite of the whole numbers in the set, you get what's called the set of integers, denoted by the capital Z. That's a German symbol from Zahlen. And in this set of integers, we talked about how it was closed under addition, multiplication, and subtraction. Because if you subtract 1 minus 4, or let's say, you get a negative number, right? And that's in the set. So like 1 minus 4 is -3, and -3 is an integer, so it's closed under subtraction, but not division, because there are no fractional numbers in the set of integers. Okay, only the whole numbers and their opposites. So what we need to do is build on this, all right? And we need to have a bigger set that includes the fractional numbers, which we call rationals. So what we're going to do is we're going to take a set, and we're going to take a look at the non-negative rationals first. So non-negatives. So non-negative rationals. All right, and that's going to be denoted by the symbol Q. And this circle's not big enough to put the symbol in there, so I'm going to put the symbol right here. All right, and it's got that little line through it, okay? And it's non-negative, so we're going to use the plus sign for non-negative. All right, that plus sign meaning either 0 or positive. So this includes 0, so I'm going to put a 0 here. And it also is only positive. If you're not negative, you can be either 0 or positive. That's what non-negative means. And the reason why we use the symbol Q for rationals is that Q is stands for quotient. And as you guys know from grade school, a quotient looks like of two terms, of two integers right here, which represents any rational. Looks like this. It looks like A divided by B, all right, where it looks like a fraction basically, but A and B are integers. Okay, so let's go. A and B are integers, so they're an element of this set here. Okay, capital Z. Integers is the set of integers. So A and B are integers, and A and B are greater than 0 to make them positive. Okay, that's what it means by non-negative, either 0 or positive. Okay, and obviously B cannot be equal to 0 because you cannot divide by 0, man. Okay, so you got these non-negative rationals. Okay, and if you take non-negative rationals, and this set right here, it's closed, okay, under addition, because if you take a non-negative rational added to a non-negative rational, you're going to get a non-negative rational. Okay, so it's closed under addition. It's closed under multiplication. All right, but not subtraction, because it's possible to take two non-negative rationals, subtract them and get a negative number, which is not in the set. So it's not closed under subtraction. And it's closed under division, all right, with the only exception that b cannot be divided, or b cannot be equal to 0. So I'm going to say it's closed under division too. You can take a divided by b, okay, as long as b is not equal to 0. So I'm going to say except, okay, or I'm just going to say not by 0. You cannot divide by 0, okay? Let's make a little exception there. All right, so it's closed under addition, multiplication, and division if you say that is you're not divided by 0. Okay? And not subtraction, okay? No subtraction, because if you take two numbers and subtract them, it is possible to get a negative number. All right, I'll just show you 1 minus 2 is negative 1. That's not in the set because, again, this is non-negative. Okay, so remember that. It's not closed under subtraction. Now, let's build a bigger set. So if you want to include the negatives in this set, you get the full set of rationals, okay, which is denoted by Q. So if you include the negatives in here, you get the full set of rationals denoted by Q with that little line through it right here, where A and B can be either negative or positive. So here, there's no restriction. A and B are integers, and they can be negative. So here it's in the form of a divided by b, where b is not equal to 0 because you can't divide by 0. But I'm not going to do any restrictions here like I did before. A and b don't have to be positive. A and b can be negative, which allows this to be negative. And if you do that, it's going to be closed under addition. Okay, a rational plus a rational is a rational. It's going to be closed under multiplication, so a rational times a rational is a rational. It's going to be closed under subtraction too, because we're going to allow a and b negative here. And if that's the case, a rational minus a rational could be, or still is rational, so it's going to be closed there. All right, and it's going to be closed under division too, with the exception of 0. You can't divide by 0, so not by 0. So just make a little exception there. Now we need to include the irrationals, and when you include the rationals with the irrationals, irrational meaning not rational, you get yet a bigger set, and it's called the set of reals. And this is everything that you know in existence, the entire number line. And the symbol for that is the capital R with two vertical lines. That's the symbol. And you can Google all the symbols, by the way. You can just type in number symbols in Google, and all these symbols will pop up. So capital N for naturals, Z for integers, Q for rationals, R for reals. Okay, you can research that if you like. Now, if you take the rationals and the irrationals and combine them into the same set, you get the set of reals. And the set of reals is going to be closed under the following operations. So closed under addition, which means a real plus a real is a real. Subtraction, a real minus a real is a real. Multiplication and division, with the only exception not by 0, because you can't divide by 0. And it's closed in a lot of other operations too. You got to be careful though, it's not closed with all operations. Make a little caveat here. Okay, not, all right, by the square root. Okay, the square root symbol. And the reason why is because the square root of -2 is imaginary, which is not real. So it's not closed under the square root operation. All right, it's closed under the cube root operation, but not the square root operation. So we got to be careful here. It's not closed under all operations, only some. Okay. Now, if you take the reals and you combine them with the imaginary, you have the ultimate set, and that set, my friends, is a set of complex numbers. So complex numbers here, and the symbol for that is the C with a little line through it right here. It's the symbol for complex. And here you gain the closure of the square root symbol. Okay, so it's closed. Oops, sorry about that. It's closed under all the operations, so addition, subtraction, multiplication, division, not by 0 though. So not by 0. I keep saying that. You can't divide by 0. It's closed under the square root operation because the square root of -2 is an imaginary unit. It happens to be I root 2. Or I can say the square root of -1 is equal to I. That's the imaginary unit. Okay, that's the best example, actually. Okay, so it's closed under the square root symbol 2, or the square root operation, where the reals aren't. Because when you square root a negative, you get an imaginary unit. Oh, by the way, let me fix this back here. I said the square root of -2 is equal to I. That's actually a little bit off. It's actually I root 2. Okay, I meant to say the square root of -1 is I. That was a little mistake. So let me just say, you can say -root 2 equals I root 2. A little easier one to handle, though, is the square root of -1 is equal to I. Okay, there's your imaginary unit. Imaginary unit. Okay, you can research that anywhere you want. Okay, the square root of -1 is always equal to I. Or you can say I squared is equal to -1. You can say that as well. Okay, now having said that, now we have this number system here. Now we want to get into classifying the numbers. So what we're going to do is we're going to take a look at some examples here, and we've got a lot, as you can see. We're going to simplify them. Simplify first. Okay, to determine which innermost set the number belongs. But we got to simplify first and then categorize it. Is it a natural? Is it an integer? Is it a rational? Is it irrational? Is it real? Is it complex? So let's get with it. All right, so here we go. So in looking at this, I get 4 minus 4 over root 36. That's the same thing as 4 minus 4 divided by 6, because root 36 is just 6. So you want to simplify what you can. We know that the square root of 36 is 6. We know that 4 sixths is the same as 2/3. So this is the same thing as 4 minus 2/3. And 4 minus 2/3 is, well, that's 3 1/3. Okay, so you simplify the expression first and then decide what it is. Now 3 1/3 is the same thing. Let me put it down here. 3 1/3. If you change it to improper, 3 times 3 is 9, plus 1 is 10. So this is the same as 10/3. And that, my friends, is representative of the rational set. It's the ratio of two integers. 10 and 3 are integers. 10 divided by 3 is a ratio of two integers. And if you look up top, it's an example of the rational number set. So if we were going to put this, this is part A right here. A would be in the rational set. I can put 10/3 here, or I can label it A, whatever you want, but it'd be inside the rational set. Okay, the set of rationals. Again, these are the fractional numbers. These are the ratio of two integer numbers here. Anytime you can represent a number as a fraction or a ratio of two integers, it is called a rational number. Okay, now part B, 2 1/3, well, that's just 2 1/3. So you get 5 divided by, all right, 2 1/3. Let's change that. 5 divided by, let me see, 3 times 2 is 6, plus 1 is 7, so this is 7/3. Instead of taking 5 divided by 7/3, I'm going to take 5 times the reciprocal, which is 3/7, and that's 15/7, and that is another rational number. It's A divided by B. So your 15/7 lives in here. It's inside the rational set. It's not an integer. It's not a natural number, because these are just whole numbers or negative whole numbers. All right, so you can't put it within the natural number set, nor can you put it in the integer set. It's not an integer, but it is rational, so you put it in between there. That's what I mean by the innermost set of numbers. Okay, next one, 4.3 bar is the same thing as 4 1/3, which is the same thing as 13/3. 3 times 4 is 12, plus 1 is 13. And that, again, is a rational number. All right, so it's rational. So 4 1/3 lives in here. Oops. So it's rational. Anytime you can write a number as a ratio of two integers, it is rational. And then you got this pi, you got the famous pi, all right, and that's 3.14159. Okay, it's an irrational number. It's an irrational, non-repeating, non-terminating number. Non-repeating. Okay, non-terminating number. Non-terminating, which means it never stops. So it's any irrational number is non-repeating and non-terminating. So it's not a natural number. It's not an integer. It's not rational. It's called irrational. So this is your most famous case of an irrational number. Okay, pi is irrational. So, but irrationals are reals. It's part of the real sets. So you can't put it inside the rational set, so it's outside of that, but inside the real set. So pi lives in here. Okay, so the real numbers include both the rationals and the irrationals. Okay. Next one, we got root 49, which is equal to 7. Root 8, which is, well, you got to simplify that. That's root, let me do it over here. Root 8 is equivalent to root 4 times root 2, which happens to be 2 rad 2. Okay, so when you simplify it, you get 7 minus 2 rad 2. Now root 2 is irrational. This is irrational. The root of any prime is irrational. And so if that's irrational, 7 minus 2 root 2 is irrational. Okay, and because of that, it lives in the real. So I'm going to put down right here, this is 7 minus 2 rad 2. It's not in the rational set, but it is real, because the real takes the irrationals and the rationals and combines them in one set. Okay, next one, the square root of the square root of 64. So you work inside out. So the square root of 64 is 8. So I simplify the root. The root of 64 is 8. And then, as I said earlier, that's the same thing as 2 rad 2, and that's irrational. So right here, we'll put down, it's in here, the square root of the square root of 64, or you can just put down 2 rad 2 if you like. Now, just because it has a root doesn't mean it's irrational. People think that all the time. This expression here, root 24 divided by root 6, is the same thing as the square root of 24 6, which is the same thing as the square root of 4, which is the same thing as 2. And that, my friends, is just a natural number. So 2 is natural, so 2 goes in here. Okay? So be careful. Just because it has a square root does not mean that it's irrational. You got to simplify it first. That's why I said in the directions right up here. Simplify first to determine what set it belongs to. Okay. Now the next one here, 2 minus 5i. That's a plus bi form. That is complex form. Oh, I forgot to say that up here too. Complex. Yeah, I didn't say that. Complex form, the form of that is a plus bi. So add that to your notes up there. Okay, right here. Complex form is, when you take a real plus an imaginary, you get a complex number here. So a is the real part and bi is the imaginary part. Okay, so complex form, you get a real plus the imaginary. You get a complex number in general. So 2 minus 5i lives here. 2 minus 5i. Now, just because an I in it doesn't mean that it's complex. People make that mistake all the time. Now, I said earlier that the square root of -1 is equal to I. If you square both sides, you get this, where I squared is equal to -1. So when you see I squared, you got to think, okay, it's equivalent to -1, and guess what? That's a real number. It also happens to be an integer. All right, so I squared actually lives here. So you got to be careful here. It's not natural, it is an integer, and so you got to be careful when you classify. So the key on this one here is to not only understand the number sets, but you have to simplify first to determine what the innermost number set it belongs to. Is it natural? Is it integer? Is it rational? Is it irrational and therefore real? Or is it outside the real set and partly imaginary? Is it part of the complex set? Now what you guys need to do is try it on your own. Okay, so on the next page here, you got some examples, and that, my friends, you're going to try that out and check it with me in class. So I'm going to leave you here. Remember, you simplify first. All right, and then determine what set it belongs to. And remember this, a new calculator, just the one between your ears. Okay, this one, the most powerful one on the planet. Okay, that was a big discussion here. Once again, I am Mr. Ainsworth here. Oops. Mr. Ainsworth. I work at Temecula Unified School District here at Great Oak High School here in MRWC. And if you're with me, I'll see you in my next lesson. Take care. Bye-bye.